The next reaction is a carbon-carbon bond forming reaction called the Wittig reaction. This reaction won the Nobel Prize in 1979, which is the same year that H.C. Brown also won his Nobel Prize for hydroboration oxidation. The product that we make out of this reaction is an alkene, and our reagent is what we call a phosphonium ylide. An ylide, by definition, is a molecule where we have opposite charges adjacent to one another. So that the structure of our phosphonium ylide looks like this. We can look at it in one of two resonance forms. The first is where we have the phosphorus carbon double bond intact. And the second is where we have the charge separation for that phosphorus carbon double bond. Now, when it comes to electronegativity, my phosphorus is less electronegative than the carbon. So that means that when I separate this double bond, the electrons are going to belong to the carbon, unlike what happens with my carbon-oxygen double bond. In the structure of the ylide, it's my carbon that has the negative charge and my phosphorus that has the positive charge. That means my carbon from this ylide is going to be a good electron donor, and my phosphorus is going to be the electron acceptor when we get to the mechanism. Now, when it comes to the mechanism, we're going to be reacting this phosphonium ylide with a ketone or an aldehyde. And let's look at the example that we have here showing the reaction take place with a ketone. In order to understand what's going to happen in this reaction, I'm going to think about splitting my ketone in half. I'm going to separate across that double bond where my carbons are going to be in one half of the product that I make, and the oxygen is going to be in the other half of the product that I make. So that's where my separation is going to be. I'm also going to separate my ylide, and when it comes to the charge separation for my ylide, I'm going to separate across that phosphorus carbon double bond. The carbon is going to be in one portion of my product, and the phosphorus is going to be in the other portion of my product. I start out with 4 components that are bonded together. And during the course of the reaction, my components are essentially going to change partners, and I'm going to end up with my carbons bonded together at the end of this reaction, and then my phosphorus and oxygen bonded together at the end of this reaction. So that when I draw the structure of that product, it looks like this. The 5 carbons of my ketone are these 5 carbons right here. The 1 carbon from my Wittig reagent is going to be this carbon right here. My phosphorus with my 3 phenyl rings is right here. And my oxygen from my original ketone is right here. So that again, I started out with 4 components that were bonded together and they changed partners. I now have the orange and the green group bonded together in my carbon-containing product that I'll carry forward in a synthesis. And I have my pink group and my purple group bonded together in a byproduct that I'll be separating out during the workup in my reaction. As you go through these reactions, be very careful with your carbons and make sure you count your carbons. So that in this product here, I have 1, 2, 3, 4, 5 carbons, and these are my 5 carbons in my product. And remember that I made a carbon-carbon double bond, so I also have an additional carbon, which is this one here, which I'll call A, in my product. So I had a 5 carbon ketone and I converted it to a 6 carbon alkene by using the Wittig reagent. When we look at the mechanism for the Wittig reagent, I'm going to start with my ketone. I'm going to start with the charges of my ketone already separated, like so. And I'm also going to set up my ylid where I have the charges separated as well. And I'm going to set it up such that my negative charge on my oxygen is going to be next to the positive of my phosphorus, and the positive of this carbon is going to be next to the negative of this carbon. Okay, so I have everything set up, and what's going to happen is that I'm going to make a bond between these two carbons, and I'm going to make a bond between my oxygen and my phosphorus. I'm going to make this bond through a cycloaddition reaction similar to what we saw with our Diels-Alder reaction. So in this reaction, my oxygen is going to donate electron density towards my phosphorus, and at the same time, this carbon is going to donate electron density to the adjacent carbon. And that's going to give me a cyclic intermediate that looks like this. So that gives me a cyclic intermediate that looks like this. And this intermediate is called an oxaphosphatane. So this oxaphosphatane intermediate is now going to undergo what's called a cycloreversion reaction, where the electrons that I use to make the new bonds in order to build this cyclic structure are now going to move throughout the structure in a different way, such that I break this ring into two components. But as I break the ring in this case, I'm going to split it into my two different components that will ultimately give me my product. So that what's going to happen is that the electrons in this oxygen-carbon bond are going to push towards the phosphorus. The electrons in this phosphorus-carbon bond are going to push towards that carbon, and that's going to give me my two products of the reaction, and my two products are going to look like this. Where I started out with my double bonds here and here, I now end up with my double bonds here and here throughout the structure. One of the things that's going to really help drive this reaction is the fact that one of my products contains an oxygen-phosphorus bond. When we talked about alcohol chemistry way back in the beginning of the semester, we learned that oxygen and phosphorus really like to form bonds. They form very strong bonds, and that was the driving force for a lot of the reactions that we talked about then, and we'll see the same thing at play here. So this oxygen-phosphorus bond is a really strong bond that's going to help drive this reaction. So I want to talk briefly about the way that we make the phosphonium ylids, like in the previous reaction that we just saw. Some of these reagents you can buy from chemical companies, other reagents you'll need to make in a lab, and their synthesis is based on principles that you already know. So the synthesis of a phosphonium ylid, like the one we saw in the previous reaction, is going to start with an alkyl halide like methyl iodide that's going to undergo a reaction with triphenylphosphine. This is going to be an SN2 reaction where my triphenylphosphine donates electron density towards the carbon, kicks out the iodide in an SN2 reaction, and the product that we make out of this reaction is almost this one. Remember that phosphorus is under nitrogen on the periodic table, so that phosphorus is happy when it has 3 bonds and 1 lone pair, so that if I use that lone pair to make a bond to my carbon, in this structure here I now have a phosphorus that has 0 lone pairs and 4 bonds, and that phosphorus is going to have a formal charge of +1. So that under the conditions of the reaction, this forms a salt with that iodide that I lost, and it precipitates out in my reaction. From there, in order to form the ylid, I need a base to remove one of the protons from this carbon in order to form my phosphonium ylid. And a really strong base that we use a lot in a reaction like this one is N-butyl lithium, which is often abbreviated like so. N-butyl lithium is a very strong base. You have to be very careful when you're working with N-butyl lithium, but it's an alkyl lithium reagent, and it looks like this. And we know that our alkyl lithium reagents, just like our Grignards, are very strong bases. We can use them as strong nucleophiles to react with a number of functional groups, including ketones, aldehydes, esters, but they're also strong bases, so that if there's an acidic proton, they can also be used to remove that proton. So that in this reaction, my N-butyl lithium is going to remove one of these protons, give those electrons to the phosphorus, and that's going to form my ylide.